Hello, welcome to this week's Graphics Programming Virtual Meetup. We follow the Berlin Code of Conduct. We have a Discord, Twitter, and a YouTube channel, of which we've uploaded the previous two sessions on this series. So you should go watch it if you missed the previous ones. So this week we're covering the 6th chapter in the VK Mini Path Tracer series. It's going to be talking about compute shaders and only compute shaders. Links to the tutorial and source code available here. We'll start with the description of what a shader is, because in previous lessons or chapters, we didn't really talk about what a shader is, just that we have them. And it's just the code the GPU runs. There's not much to it beyond that aspect. In Vulkan, you only are able to give the API SPIR-V, which stands for Standard Portable Intermediate Representation -V, which either could be Vulkan or could be visual. I'm not sure which, but I would bet it's Vulkan, because SPIR is was a thing before Vulkan, and it was mainly used in OpenCL. While SPIR-V is a binary format, it's like machine code, though it's a little bit higher level. It is not written by humans. We tend to write GLSL or HLSL, which are two shader languages. Both have C-like syntax. The code we're going to be writing today is literally this text box here, but just as an example, you have the pounds here for defining macro-like stuff. You can see a versioning and an extension thing. Then we have this layout qualifier, which you can think of as our inputs in a sense, but we'll talk more about that in a bit. And we have a main function without the arguments like there would be in C, because that doesn't exist in Shaderland. But then we have this function call, we have a string, and we have this global variables with a .x and a .y. So while this isn't a tutorial on shader languages, I will try to explain the gist of the things we're writing. So shaders are code that gets run on the GPU, but unlike CPU code, they have a very different programming model. They're categorized as single instruction, single program, multiple data, or multiple thread, SPI, SPMD, SI, MT, any of those variants of that classification would apply. If you run a shader, you never run one. You always run the same shader on many hundreds or thousands of data points. So in a traditional graphics pipeline, you have a shader that runs for each pixel on your screen. So that might be, if there's 1,000 by 2,000 or 2,000 by 1,000 pixel screen, that's going to be 2 million times, something like that, if you were doing it per pixel. The biggest difference between the different shader types is not just things like the availability of different global variables or inputs, but really the method in which, or the mechanism in which they are invoked. As in when and where and how do different shader types get invoked versus other ones. In a classic graphics pipeline, there are just two main shader types, a vertex shader and a fragment shader. The vertex runs per vertex in each mesh, and a fragment shader runs for each pixel you're trying to shade. But that is classic. We're dealing with modern, where we're doing things like compute shaders, which is what this entire tutorial uses, and that's a general general shader that can do most anything. It also has the important aspect of being able to control when and where it gets invoked, unlike vertex and fragment, which are dependent on the number of vertices or the number of pixels that need to be shaded. With the RTX extensions, there's a whole new category, the ray tracing category, and that's the listed here as the ray generation, any hit, callable, close it to intersection and miss. Each of these shader types are shaders that get run based off whether a ray hits something, misses something, goes through a medium. Like any hit would be, it doesn't matter what you hit, and intersection for when you hit something. Closest hit is the closest thing you've hit. Like all these different shaders get bundled together into a shader binding table, or any sense it's a group of shaders that, when run together, ray trace the scene. We're not going to be using those in this tutorial, though there is an additional chapter describing it. With the things I didn't mention are these graphics shaders, which are fancy and fun, but really are just more fine-grained control over the vertex shader, in the sense that they allow you to create new vertices or modify existing ones in ways that the vertex shader wouldn't. I have the lineup here organized by which pipeline they run in, and that's because these are the 3 different pipeline types in Vulkan. You have a compute pipeline object, a graphics pipeline object, and a ray tracing pipeline object. And the shaders and the categories can only be used in those pipelines. So it's not just a helpful distinction, it is a purely mechanical and necessary one. So there's a feature we're going to be using called ray queries. It is possible to use them inside ray tracing shaders, but also are usable in compute and I believe pixel fragment shaders. We're going to be using them in a compute shader, and the main reason we're using this capability is because it's easy. Ray queries means you don't have to set up the ray tracing pipelines, any of those shaders. You don't have to set up all of the different fancy things like access to line bounding boxes and BVHs and all sorts of fun stuff that would make a ray tracing pipeline the ray tracing pipeline. Though the downside of doing all that is it takes a lot more code, so that's why we're avoiding it. While we don't use the functionality in this chapter, ray queries are kind of like a function call. The ray query function, you call it inside the compute shader, and then you get back whatever the ray hit or didn't hit. A important part of compute shaders compared to all of the other shaders is that control over invocation. In, say, a vertex shader is invoked on every vertex in a mesh, where invocation is the term to describe you're calling the code given a set of data. So in each invocation gets its own set of data, because on a GPU, you run the same shader many hundreds or thousands of times in a single invocation, or not invocation, dispatch. So we need to have a mechanism in which to organize all of these invocations in the compute shaderland, because they, well, otherwise wouldn't exist. And that's important because we have to know what data to address in the shader. In a vertex or fragment or even the pipeline, ray tracing pipeline stuff, whenever you invoke a shader, the API is set up so that that shader knows what's going to be put in. In the case of a vertex shader, it knows the vertice data that's going to be fed in. And so the shader just goes, here's my data, I will operate on it. In a compute shader, each compute shader invocation doesn't know what memory to access, what textures to look up or write to, or where to write them in. So you have to provide that information yourself. A spanner in the works would be that when you run a compute shader, it's not a single, you run one command and everything happens all at the same time. What you actually need to do is you need to specify a more or less 3D coordinate for each invocation to use. When I say 3D coordinate, there's two 3D coordinates that are referred to. There's the intra work group size and the extra work group, meaning where are you inside of a work group and where are you, in which work group are you in? That's because a GPU, while it is supposedly many hundreds or thousands of hundreds of thousands of little cores, almost always they are grouped into sections of maybe 32 or 64 or other powers of two sizes, usually 32 though on NVIDIA cards. And if you try to run something and you don't utilize all of the individual workers inside of a work group, as the division is called, you're going to be underutilizing the hardware. If you imagine a GPU as a giant SIMD machine, you have to make sure that the work you are giving the driver matches what that GPU is capable of. And not just capable of, but what is optimal for it. Fine-tuning what that value would be, how you divide up your work, it's not trivial. There's a lot of green text in the text of the tutorial, green text being the notes and additional info that is possible to skip, but you really shouldn't, and you should read in to get a more broad understanding. It talks quite a bit about it, and for anyone trying to seek the fastest performance, you should definitely research and understand more of the nuances going on. Choosing different work sizes, work group sizes means different speeds of your code, or occupancy is the imperative word here. But I just threw a bunch of words at you and that may not make any sense. So a better visualization of what I mean is using a simple example of trying to multiply every element in an array by 2. So imagine we have an array of 15 by 13 floats. Each of these floats has a value in it, and we just want to multiply everything by 2 so it has twice the original value. Because of these work groups, we want to split up our work into chunks of, well, a power of a multiple of 32. So we're going to take our data over here and we're going to split it up in not half, but the first is we're going to have the first 7 rows in our first work group, and the remaining rows in the next work group. So it's a bit hard to picture, but imagine the left side box being put on the right, and then the bottom space over here, if you can see my mouse, that's missing, would just have nothing happen to it. So we're going to have our work groups individually work on a 16 by 8 chunk of it, but then we're going to have 2 work groups. And in this case, it's a vertical arrangement like this. So we're going from 0 to 7 and then 8 to 16 or 8 to 15. And the reason, sure, performance is important and you want to utilize the hardware the best you can, but what kind of cemented this for me was the fact that each shader invocation doesn't know what data to access. When you specify this work group stuff, it means that the shader can be written such that you do GL invocation ID. We saw this a bit in the first slide with the code in it. We use that as our index into an array because we make it so that there's an array of X size and that every index into it can be done without doing an out of bounds access. So all this is really doing is telling the shaders, it's not all it's doing. The main thing we need it to do is so we can tell the shaders, you access this memory, and the shader will see that and go, ah, yes, okay, I have my GL invocation ID .x. That means I look in this column, and then the .y look in this row, and then .z looks at this z value. For what we're doing, I believe we're just going to stick to 1 dimension z because we have a 2D image we're rendering to, so we can stay in nice 2D land rather than 3D where we have more access. But moving on, now we get into the fun part of creating our shaders. So we simply create a folder called shaders. We make a new file with this name in it. It's important that the .glsl is at the end because that's the extension specifying that this is in fact a shader, a GLSL shader. We have our name, and then we have .comp, which just says what kind of shader it is. This is informal syntax in the sense that there is no standard in which a shader must have a certain extension. I mean, there are conventions, and this is one of them, comp being a shorthand for compute. We want to add this text into it. We have our version number. This would be 4.6, but without the dot is 460. This layout thing is the work group size, except it's the intra work group size, where we're going to have 16 and 8, and then 1 as our D dimension, and that's what the in specifies. I don't have any slides explaining shader language specifics. If you need more, and neither does the tutorial in great depth. If you need more information, do look up GLSL shader tutorials. So when we add the file, we need to regenerate the CMake and rebuild and then run it. And this should automatically pick it up and create a shader.spv, shorthand for SPRV. So this will be our binary file that gets compiled. So the shader we want to write first is just a hello world. We have this handy debug printf ext, and we can give it a string, and we can print hello world because we're like every other intro to programming tutorial where hello world reigns king. Now, this will likely print 128 times because we're running it in 128 individual invocations, and that means each shader is going to try to write hello world to the output. Except we haven't implemented any of the code necessary to make that happen. This is just the text for it. And this is, for reference, the way you enable extensions in GLSL, where you have pound extension, the extension name, and then you can add a require here to require it to mandate that it's needed for the shader to function rather than being optional or some conditional thing. So we've talked about shaders as code, but we haven't really talked about how they become code. It's extremely similar in the mechanical steps as far as code goes to a normal, like a host language like C++, Rust, static languages, that is. Actually, there's actually a lot of parallels to something like Java or C#, which has an intermediate format, a bytecode format. It's actually more closely related to that now that I think about it. Anyways, you take your text file, your GLSL or your HLSL, you run it through a compiler. We often use GLSlang validator, which is a command line application that comes with the Vulkan SDK, and it produces a SPRV file, which is bytecode. It's a bit like ASM, but a bit higher level, and it's meant to make it easy for drivers to ingest and quickly turn into the actual assembly code that's going to run on the GPU. Because GPUs like to ingest shaders, but they don't actually run GLSL directly in like an interpreter or something. They run assembly, like every static language. So that's why it's similar to Java and C#, where you have to put it into an intermediate bytecode format that then gets compiled just in time for the actual drivers to use. There's a real benefit to doing this, and that is because you can change the assembly, you can change the driver to make it optimize better without having to recompile the shader in the first place. And that makes it easier to take a game from 10, 15 years ago and run it on modern hardware and get the benefits of that. Contrast this to CPU's SIMD instruction sets, which are more or less baked in stone, and every 2 generations of CPUs you get a new SIMD instruction set, and now programs have to write in explicit code paths to take advantage of it. That doesn't have to happen on GPUs because the compiler inside the driver that turns your SPRV into bytecode will do that for you. You can optionally view the SPRV directly. There's a disassembler tool, SPRV dis. They'll show you just the raw bytecodes. If you use RenderDoc, you'll find that it has a view in different nicely formatted forms, and one of them just turns it back into GLSL, which is kind of cool. There are ways to see the ASM of a GPU. I know NVIDIA has one for CUDA, and AMD has a mostly public assembly form and that you can see directly, which is just nice because if you want to make something fast, seeing exactly what the assembly is very helpful. But we're not really here to do that, so I'll leave that to everyone who's watching to do that on your own time. I didn't exactly mention how the shaders get compiled because I just kind of said they did. We use CMake, and CMake has some magic in it to make it possible to pick up files and then compile them automatically, in the sense that we wrote a bit of CMake code to make that happen. And by we, I mean the tutorial, the framework. In the CMake files, there's this blob of code which globs and finds all your shader files. So it will look for anything that ends with GLSL. So that's why the extension is important in this project. And then for everything it finds in there, it will call this GLSL variable, which is the name GLSlang validator, and it's going to be platform specific. There's a little function here that wraps it up. It's a whole bunch of CMake to make our lives much nicer. If you are making a big rendering engine, this is something you'd probably want to integrate into the code rather than into the runtime code rather than compile time only. That way you can do runtime code reloading, so you can change the shaders, then reload it quickly instead of having to close the application and then let the build system do that. But that's for more fun things in the future. For now, we just call GSlang validator on each shader and we let that happen. To make a compute shader takes multiple objects, and those objects are, in a sense, a small directed acyclic graph, where the VK pipeline is the big fat honkin' object that holds all of the things necessary to start a shader invocation up. To do that, it needs to know the pipeline shader stage info, which itself holds a shader module. But the pipeline also needs to have a layout, but we're not using it this chapter, so it's going to be empty. Starting from the top, we need to update the header, well, the top of the main.cpp to add additional headers, the file operations, and then shaders. File operations helps us load files like the SPRV file, and then the shader ops is for shaders, which I hope is self-explanatory. We're going to, in this chapter, use the debug printf capabilities, but by default, it is not a thing that's implemented in drivers. It is implemented in the validation layers. So while almost every host language like C++ has some capability of printing to a file stream like standard out, in GPU land, that standard out doesn't exist. What we have to do instead is create our own place to write messages, and that place can then be put in GPU memory, and we have to write code to, well, there has to be code to write to that buffer and then read it back on the host and then write it to the actual standard output of the process. Thankfully, the validation layers have done all of this for us, and all we have to do is enable the feature. The validation feature enable debug printf. We do that by adding a VK validation features ext struct to the pnext chain. Oh no, of the yes, we add it to the device info creation struct, and I believe this is an NVVK helper thingy here. So rather than having it add it to a pnext chain, we can use a more direct enable thing. And this here is just to set it to print a standard out rather than to a debug callback. Since it uses an environment variable to set that, we need to set an environment variable, and thanks to Windows and Linux having different conventions, we have to use platform define to get that. Notice up here we have this extension here called shader non-semantic info. In SPIR-V, it's a bytecode format, and shaders are mostly just math. They're just, you have a matrix, you have a vector, you can multiply them, you take the result and you throw it in a vector over there. Well, non-semantic info is things like variable names, function names, things that a compiler could strip out, and, or in our case, debug printf, which if you're trying to make your code fast, you would not print anything. But if you're trying to debug it, like we kind of are, you kind of need that. And well, this extension is just required to make the feature work. So we're not going to use this we're not going to require debug printf in future chapters, but it is a very handy tool for debugging. But I mentioned RenderDoc earlier, which is a graphics debugger, and it is also helpful for debugging. So to each their own. I probably would use RenderDoc first because it just provides a more holistic view, but that's neither here nor there. So to make our code a little bit more legible, we want to add a workgroup width and height variable to the near top of main.cpp. It's just to get rid of magic variables. We don't really want those. So now we can actually start creating the Vulkan objects. The VK shader module holds the SPIR-V file, SPIR-V data. SPIR-V is a bytecode format, but it is represented as an array of uint32 values. So it's just an array of 4 ints, unsigned ints. So when we load that, we just load the array, and then we give that array to the driver and get a VK shader module back from it. We still have to provide a bit more information about it, but not much. Actually, I don't think there's really any other information in it. I'm trying to remember because it's such a basic thing. I can't remember. I need to look up VK create. Yeah, I'm sorry. I just blanking on the details of the create info. Okay, there's flag. Yeah, okay. The only other thing in it is a flags, which I believe has nothing in it. Yeah. So it's literally just the data. So yeah, VK shader module is just a fancy way of doing a array that the driver owns, so the driver doesn't have to worry about it being freed on it accidentally. But that's not telling you about this big long search path thing. So because we have to load the shaders from a file, we have to tell the program where that file is located. We have this search paths thing here because the shader could be in multiple places. Now, we see here it's in shaders, excuse me, ray trace, this folder we just made, the SPV file. The thing is, this will not just be used for shaders, it will also be used for OBJs. I don't know if we're going to load textures, but I imagine that'd be useful for that. So this is really just a whole bunch of places we might look for data. And so it's nice to have it search multiple places so you don't have to wonder, do I put it in this folder or do I put it in the parent or in that folder? And so it's just convenience. And there's another NVVK helper function, create shader module. The main gist of it is that this load file does the heavy lifting of loading the file, copying the data into an array, and then passing it to, and then VK shader module passes it into the driver, and then you get the VK module handle back. So let's create a pipeline shader stages create info, which takes a shader module, you add in the shader stage, you tell it which function is going to be the entry point, and then it gives you a shader stage. Actually, it doesn't give you a shader stage because this is fed into the VK pipeline struct. I got ahead of myself. We need to tell it the entry point, because while main is a convention, in Shaderland you could have multiple functions and just simply tell the shader stage create info that, by the way, this time I want to use this function as my main one. Oh, and this time I want to use that one. It's one way to do code reuse. It's also another way to do specialization. So if you have the same shader core, but sometimes you only want some of the features and other times you want other features, you can have two functions and then both set up what's needed to call into the core and then do what's needed, but they have different names, and this is the way you can specify that without having to create separate shader files and compile those files into SPIR-V. Since we're using compute, we have this compute shader bit. If you were using a different shader type, you'd have, stage, fragment, stage, vertex, ray tracing, all that fun stuff would go there. There's a flags variable you can set, has some additional stuff, but we're not using it, so we don't say it. For whatever reason, the auto highlighter picked up module, even though in this context it is not a keyword. So if anyone's familiar with the C++20 modules, they'll see that this keyword is a thing and it is not applicable here, but the syntax highlighter doesn't know any better. So I'll give it a pass. I'll try to quickly summarize the VK pipeline layout because we're not using it this chapter, but we're not doing anything with it this chapter. It is the description of the inputs to the shader, the non-global variable inputs in a sense. Global variables being things that are in shader in GLSL always defined or already defined, depending on the pipeline type. Like the GL invocation ID I mentioned earlier is a global variable because it's not global in the every shader has access to the same version of it. It's global in the sense that every shader has it regardless, even though it's going to be different. Because we don't have any actual elements in there, we just create an empty pipeline layout, meaning there's no layout, there's no count of layouts, and so we don't have to provide a pointer or anything. And these push constants, which I'm not going to explain, also we have 0 of them, so there's nothing there. We create the pipeline layout and we get the handle to it in this pipeline layout object or handle, and then we use that in the next part where we create the compute pipeline. So I wanted to, the tutorial text usually shows this struct definition before using it and has nice comment annotations. I wanted to show it here because I could have done it before, but this one is more here to contrast with graphics pipelines and I believe ray tracing pipelines, in that we have the two common Vulkan members, the S-type and P-next in the first two places. We have a flags if we have additional things we want. We have to provide the stage, which is the thing we made that describes what the shader module is, where it is, and the name of it. And we also have the layout, which has nothing in it, but we still have to have a valid object. It has these two final things, which are meant for pipeline derivatives, which are a way to supposedly speed up shader computation, but we don't use them. And I haven't used them personally. I should look into it, but at some point, just so I'm more familiar with the concept. But I just described you all the variables. If I was doing that for graphics pipeline, we'd be here for another 20 minutes because it has like 15 members, and each of them are kind of complex because they're almost half of them are required for a useful graphics pipeline, and the other half are things you have to say, I don't use this feature, I don't use this feature, I don't use this feature, but you still have to provide them, and that's very annoying, and there's a lot of members, and it's a very annoying process. Compute pipelines are much simpler, moral of the story. So to actually use it, we follow the very common create a info struct, fill it out with our details, and then call vk create our handle struct thingy, and we give it the context. We give it the number of create infos, excuse me, I'm sorry, and the address of the first one in the array. We don't use a allocator, and then we get our handle to the compute pipeline back in the object we have by giving it the address of. You can notice that it says pipelines instead of pipeline. So we could create multiple compute pipelines in one call. You can do the same with graphics and ray tracing. That's handy because you can say, okay, I need to create 10 pipelines. Here's all of the information driver. Do what you need to. And so there's not many calls that let you create multiple objects at the same time. The asterisk is that you can allocate multiple command buffers and descriptor sets at the same time, but those are not objects you create. You allocate from a pool, which is different. So this is the most interesting line here in this call because we haven't talked about it yet. The allocator we can ignore, but this pipeline cache is a mechanism in which to speed up subsequent creations of the same pipeline using the same shader. So you can create this cache, and the driver will put all of the created pipelines into it. Then when your application closes, you save that cache to a file, and then when your program runs again, you load that cache up, and the driver will go, oh, I've already compiled all these for this current driver version, so I'm going to take all of the things out of the cache and use it. It mentions its default, which is simply that there is no cache, so the driver doesn't use one. Though I've heard mention of some drivers doing this automatically, as in they do it inside the driver for you, which is interesting, but these pipeline caches are a common way to help speed up subsequent runs in most applications, unless your driver does it for you and then you don't have to implement it yourself. The driver did it already. But I digress. So yeah, we just fill out the create info struct, we call create compute pipelines, we give it all the handles, we get the data out of it, and we have a pipeline. We also have to make sure we successfully created a pipeline, which is, this macro hides all that fun stuff. So we have our pipeline. Now we want to use it. We need to delete all the fill value and vk fill buffer commands. We replace it with a binding of our compute pipeline we created, and then we dispatch the shader. Mind you, this code is happening inside the record command buffers call, not not outside of it, because otherwise there'd be no command buffer in which to write this. So we bind it at the compute point, because a pipeline, notice it's just a pipeline, not graphics, compute, or ray tracing. So this is how we specify which, pipeline area category we need, and then we give it the pipeline we want. So command dispatch executes our invocation. It invokes our invocation. And you'll notice it has 1, 1, 1. They're literally just group ID X, group ID Y, group ID Z. How many in each axis do you want? It's interesting to think about invocations as like a 3D point, a 3D matrix. And then it's funny to see that the API even basically explicitly calls it that, even if on the hardware it's, it's a bit different because the hardware isn't a matrix properly. It's not actually 3D, but the way you address it tends to be 3D, and that's the most ergonomic way to do things. Because you can map a 4D thing down to 3 or 2 dimensions if you really need, but 3D tends to be the most simple way to address everything. So now we're actually running our thing. Hello synchronization, my old friend, we need to update the barrier because we are no longer using the transfer operations, we're using compute operations, and will be for the rest of the tutorial. There's only 2 things we need to change. The gist is we're changing transfer operations to, compute operations. What we're really doing is we're changing the source of the memory writes from the transfer part of the chip to the compute part of the chip. So we have to tell the source access and stage masks that we're going to be using the shader writing rather than the previous one, which I believe was transfer transfer finish, or whatever the equivalent of that is. And for our stage mask, meaning what pipeline stages like is just compute. So it's, if you look at the text of the tutorial, it highlights these changes, making it a lot easier to read. But can I do multiple highlight? Yes, I can. It's these two lines that get changed. We're still going to be using a host read to get the data back, and so the host is the same on either end. So that's the only things we change, but that's very important we do that because otherwise the write sign might not finish in time. And of course, we always want to clean up after ourselves. We just need to delete the 3 objects we created: the pipeline, the shader module, and the layout. Do this before you just destroy the context. And that's about it for that. If we're successful, we should get this very long message that prints out "Hello World." Woo! It might print it out multiple times, depending on how many invocations you invoke, 1 or 128 or whatever number. All this additional information is, well, additional. Printf telling us it came from the printf rather than from validation, because this is implemented in the validation layers, there's quite a bit of other things that can print out messages, and so this is to delineate that. Some fun hex numbers to think about, but we get our message. We're actually getting a shader doing stuff rather than just rounding values. But let's make it a little more interesting. Let's use these global variables I kept talking about and print that. Since debug printf uses a printf-like formatting, we can use the %d to print out numbers. So we call the function, we give it the 2 numbers we want: global invocation x.x and then global invocation id.y. So we just need to change our shader source. We need to recompile the program so that it compiles the shader. And now we should get a hello from invocation x, y. And if we wanted to print out the z, we just add another %d and then add the variable, so that'd be comma gl global invocation id dot z. So here, that's the this is the global variables I was talking about, where every shader has them, whether they declared them automatically declared for them, which is akin to globals, where they're just always present. Globals in like C or C++. If you do this with multiple invocations, it will not likely be in order. There will not be 00, 01, 02, 10, 11, 12. It won't be like that because the shaders are running as fast as they can, and whoever gets the lock to write to the debug printf buffer gets to write it first, and that's whoever gets it first goes. So that's everything we have this week. I hope that was a gentle introduction to compute shaders, both their basic theory and compiling them and actually using them. I know I didn't go into too much detail about the language itself, but I'm not the best teacher for that, and neither does the tutorial go over in great detail. So are there any questions? Yes. Need some water.
Cool, great. Yeah, it was very interesting to see the differences between parallels to between this and what OpenGL does.
It'd actually be probably good of me to look at doing this in OpenGL just to see where the little differences are, because while the means and ways are probably the same, there's some things that are different, and I don't know what they are.
Also,
you set up a pipeline. You just invoke basically.
Oh yeah, cool.
Yeah. I was
Yeah.
just going to say thanks again for helping me with the CMake stuff the other day.
Yeah. Just finishing off, we're going to be talking about descriptors next week. I looked at the chapter and went, yeah, I could talk for 35 minutes about that topic alone. So, and then the next chapter is actually getting into proper ray tracing stuff rather than just Vulkan basics and stuff. So, I think that's end of everything. I don't see any questions. So, yeah, thanks.